Okay. Um, let's get started. Okay. Okay. All right. Well, let's start recording. All right. I'm not sure. Okay. Everyone can see my screen? Yes.
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 Okay, cool. So, all right. There's a couple topics you guys gone through first four chapters, correct? Have you been doing the in PowerPoint skill builder questions? And also, have you been reading the textbook? Are you guys practicing via text, via past exams? Because I just basically screenshotted all the questions that Eric sent me, plus two exams, which I could go for the full 2 hours and do all these questions. But if anybody has questions from the textbook, from another organic chemistry resource, or just more general questions about like, oh, hey, I just don't understand resonance or Orgo, I guess I can walk through it. But I would like for this to be as much as a group participation. Um, I mean, there's little breakout rooms that I could do if you guys have your ads or something that you can share with, which would be extremely helpful. If not, I could just jump into problems and, we can go through each one of these one by one together as a group. Does anybody have a preference? Does anybody care? That's when you turn your microphone back on.
I think
Like,
it'd be nice. I think it'd be nice to go through problem by problem together. Thank you.
Okay.
And I know in class we talked about the topics that most of us wanted to practice was resonance and I think some Ario.
Okay. All right. So let's do resonance Ario as main focus, and then we'll leave boiling point and naming as like lower priority. So significant resonance structures, following compound, what's going to happen? There's a conjugated system with a couple of sp2 carbons. Do we all see, can we smell resonance by this point? I'm not sure if you know what I mean, but do you see pi bonds moving at this point? Does this make sense? There's like a little like idiom or saying like a pawn becomes a bear, a pawn bond becomes a pair becomes a bond. But I'm basically jumping between whatever carbon, if we call this carbon 1, 2, 3, 4, 5, 6, 7, instead of going and drawing all the intermediate resonance structures, for example, this pi bond can become a pair here. So there's going to be a little bit more electron density here, but that negatively charged carbonyl will then again become a bond. So I'm just jumping with those pi bonds from basically adjacent carbons. Does everybody see that?
Yeah. And do we do each movement one at a time, even if it takes like 10 different resonance? You have to do it
You
one at a time?
you could. The point of the example for the questions he's going to ask is like, do you know what's the major contributing resonance structure and why? And basically, it's because whatever is holding the negative charge is either more polarizable, if you know that word, a more uneven distribution of charge because of a greater electron density or greater p orbital, if you will, or because it's the negative charges on the more electronegative atom. So whatever has the negative charges, it's because it can, comparing carbon to oxygen, oxygen is going to end up having the negative charge because it not only is it more electronegative, but it's bigger than carbon. if that makes sense. So I'm obviously not going to draw all these structures, but that's why, like for the first one, I just want to show you what the major contributing resonance structure would look like. So it would look something like this. So essentially we have one less pi bond, but we still have a better resonance structure. This molecule is flipping between both of these. So in the sense that it's neither one nor the other. If there's resonance to be had, there will be resonance, if that makes sense. And this is based on like localization of the electron pair, or the electron, lone pair. If you see a nitrogen that has that electron lone pair in an sp3 hybridized orbital, and it would either break aromaticity or it would not be able to donate into this conjugated pi system, you won't normally have resonance. I don't know if Eric showed you an example of like a nitrogen. Let me see. If you had nitrogen that looked like this, maybe, but it's lone pair here, and maybe something that looked, I don't know, something similar to this would probably look like this. And when we ask you that, is that lone pair in resonance? Does it have resonance? Or is it in, so the question is that lone pair delocalized or localized? Does anybody know the answer?
Would it be localized due to the pi bond on the left?
Yeah, I mean, so the yes, I mean, like that's the short answer is like yes, it is localized. You would have to have another group on here to make it delocalized because it can't just donate without having like this. What is this, sp2 or sp3?
Two.
sp2, right? Usually with sp2 we'll be looking at delocalized, but there will be sp2 examples that that lone pair is localized. And so this is just giving you like I want you guys to think via hybridization, via what's being pushed around, whether it's possible. But we'll have plenty of examples. So I'll probably show you that in another question. Let's
I
do
have a question.
this. Go ahead.
When it comes to, can you please go up a little bit? When it
Sure.
comes to like writing constructing the resonance, why is it more ideal, for example, in this case, to move in this direction instead of the opposite direction?
Well, if you were, I mean, if you're saying to move, I don't know, like if instead of pushing that pi bond up and we were pushing all these bonds the other way, we're comparing the two atoms. So if I decided to push this way, you're saying, right? You end up with a positive charge on the oxygen, do you not? And then if I decided to push this to either carbon number 6 or the bond between carbon number 6 and 5 or whatever this number is, I think this is 4 actually, and push this here, and then let's say push this pi bond here or here. Well, guess what? Now your negative charge is going to be on a carbon, and you're going to form a positive charge on an oxygen. The number of charges matter. Like you want the least amount of charges in your resonance structure, if it's possible, or you want the negative charge being on the most electronegative atom. Here we've made a positive and a negative charge, and we also have that positive charge on the more electronegative atom and the negative charge on the least electronegative atom. It's going to be less stable, and it's going to want to shift the equilibrium such that it's going to have the negative charge on the more electronegative atom.
Out of those two examples, the original and the later on, and which one is more stable?
So it's basically between the original parent structure and its resonance. Here, the original has less charge, so that in theory would be more stable. But if you had a question, like, and he's telling you to draw all the resonance structures, I mean, you could pick the first one, and in some cases, the first one will be the one that is also most stable. But in this case, it's the one with the oxygen with a negative charge versus the carbon with the negative charge.
Okay, thank you.
I have a
Okay.
question. Why don't
Go
we
ahead.
put the lone pair surrounded with the oxygen, the right side, the structure?
It's represented by this negative charge. I'm making the lone pair. I'm not implicitly drawing the 3 lone pairs. But if I told you to calculate the formal charge on this oxygen, what would it be? You guys know how to calculate formal charge, correct?
Yeah.
Yeah,
It'll be
it's
one.
-1.
Yeah, exactly. So that's why I just drew the negative charge. And for anybody that doesn't know, formal charge is quickly, it's valence electrons minus dots minus sticks. You know, Chem 104. But just in case you didn't, 6 valence electrons that it's supposed to have has 6 electrons or dots minus 1 bond equals negative. Okay,
Okay, thank you.
you're welcome. Okay, Hamilton is a hypnotic agent used to treat insomnia. Okay, let's look at the molecular. What is the molecular formula of this compound? We could skip this question. You won't be asked molecular formula, but you can obviously just count the carbons. I feel like this is a tedious example. You would count your carbons, whatever that is, carbon to the X, count your hydrogens, and we all know how to count hydrogens by this point, right? This is a very
Yeah.
quick course, so you know, you have your methyl groups, you have your methylene groups, and then you have your methionine groups. Basically, all that means your CH3 groups. So CH3, you know, I'm not going to go through all these, your methylene groups, and either like your other functional groups or, so we call these a different kind of name, but the ones that only have 1 hydrogen. But you would see, I mean, in this case, all of these have 1, but they're your vanillic hydrogens, if you will. Count all your hydrogens, and then you just write your formula. I mean, it's pretty simple. Okay. How many sp3 hybridized carbon atoms are present in this structure? By the way, you guys can stop me. Did you do some of these questions in class? Because the ones I saw were the empty ones. And if you guys are like, oh, I already practiced this, or you did this in class, then you know we can skip over these. But I'm just gonna try to triage what's most important. So sp3 hybridized carbon atoms present. This is a okay question, but anybody quickly, where are the sp3 hybridized carbons? I believe you guys can also annotate if the drawing feature is enabled in your computer. No? Does anybody know how to view sp2 hybridized or sp hybridized carbons? Do we know what that is? Do we know how to get there? Do we remember Vesper theory?
Steric number.
Steric number, yeah. Or electron groups, sure. So whoever just spoke, what is this? Is this sp3 or sp2, sp,
SP3.
sp3 here?
SP2.
No, it's sp3 because there's 2 hydrogens here, right? So it has 4 groups. It's connected to another carbon, 2 carbons actually, 1 carbon here, 1 carbon here. That's sp3, right? Just do the like whatever group. So it's if it's 4 groups, sp3. If it's 3 groups, sp2, sp2. If it's 2 groups, it's sp. And these different percentages just represent how much electron density we're pulling from the p orbital to the s orbital. And as such, we can make a determination on whether like, oh, okay, if something is sp2, it's more likely to be whatever, like whatever bond angle. If it was SP, more likely to be and I don't know if you guys understand why that is. It's based on hold on. It's based on taking away electron density from something. It's the hybridization theory. One is more symmetrical, the other one, or more spherical, the other one is more linear. So as you take equal amount of densities, S density and P density, you end up getting a more, for example, in the SP case, you end up getting a 180 observed bond angle. And the reason why that is because you're using 50% P density, which is just, it's like the Cartesian plane. It's either Py, Px, or Pz. So you're using like 50% more Px, and that's making this 180-degree bond angle. But I'm not going to get into, I'm not sure if he talked about that. So just keep that in mind, because that comes back when he talks about like, oh, is this nitrogen sp3 or versus sp2, and what's its observed bond angle? And I think there's a question like that in here. Yeah, we can identify the geometry on these. So sp3, 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 and I think that's it. Does anybody else see another sp3 molecule? Or carbon rather?
What about the one
No?
right in the like really dotted, like heavy line?
Here?
Yeah, yeah.
Well, okay. Is there a hydrogen here?
Yeah, there's one
Carbon has
hydrogen.
carbon has 4 groups, right? So since it has 4 groups and there's a hydrogen there, it's connected to 3 carbons and a hydrogen. Is that 4 electron groups? Is that 3 electron groups? Or is that 2 electron groups? Four, right? So that would be sp3. You see what I'm saying?
Oh yeah, yeah. It's because you didn't circle it. That's why I was asking.
Oh yeah, it was sp3. My bad. I didn't circle it. Yeah, you're right. I thought you said it was sp2. I'm sorry. Okay. sp2. Anybody?
The ring.
Or do we? Yeah, the ring, basically. So all these structures, we count the pi bond as one group. So this has 3 groups. This technically would have 3 groups, 3 groups, 3 groups, 3 groups, 3 groups. Okay. What
And
about the
that one
carbonyl?
carbon by the
Yeah.
by the nitrogen and oxygen, right?
Yeah, the carbonyl carbon would also be sp2. And that's an important point. We call that the electrophilic carbonyl position. But there's slight like if this is electropositive, this would be electronegative. And that makes sense, right? Because the oxygen is pulling electron density away from carbon. Its electronegativity is like 1.68 difference. So yeah, sp2. Do we see any sp atoms on here?
No.
No, right? Cool. All right. How many lone pairs are present in this structure? Obviously the lone pairs would only be on either the oxygens, the nitrogen, or this oxygen. Okay. How many lone pairs? I mean, that's an easy question. Okay, and so this one is like, where is it localized? Where is it delocalized? Okay, can you tell me which lone pairs are localized or delocalized and why? Maybe if I
The
erase this,
nitrogen
I'll
lone
make this easier.
pairs, the nitrogen lone pairs are delocalized. The oxygen on the ring is delocalized, but the oxygen with the pi bond is localized.
Can you tell me why?
Yeah, so why they're delocalized or why the one is localized?
Why the two are localized?
So the oxygen with the pi bond is localized because the electrons wouldn't have anywhere to go because of the pi bond.
You're talking
And
about these. Yeah.
Yeah, and the nitrogen and the other oxygen, the one that's on the ring, are delocalized because they have was it allylic conformation or something like that, I think.
Yeah, so there's a little resonance stability based on this pi bond. So instead of pushing this pi bond like to this position, we could also technically have pushed it to this position, right? And then you get a negative charge here, and you can have you have a positive carbocation. You push this lone pair here. In truth, it's less likely to happen than in the nitrogen case, just because nitrogen, you'll learn that nitrogen is the better pi donor. And so because it's the better pi donor, what's more likely to happen, you're still right, by the way, is this nitrogen's lone pair being delocalized and being pushed up, where instead of, I'm not going to draw the whole structure, but what you get is nitrogen with a double bond here, hydrogen still there, but now you get, move this. Yeah. Why is it not doing it? There you go. So you get something that looks like this instead, and this would be more contributing to the resonance hybrid than in the first case. Does that make sense? Nitrogen's a better pi donor. It's less electronegative than oxygen, so it's more likely to have a positive charge. That lone pair is delocalized. You can view this as, since both of them now in this case are sp2, you have an empty, I don't want to confuse you guys too much, but you have an empty p orbital right here and right here. Because this sp2, right, trigonal planar, you have a p orbital above and below the plane. And so above that nitrogen is an empty p orbital, and that other hydrogen is back here. I'm not showing you, but the other hydrogen is still back here. And so it's planar. Those p orbitals are coming above and below the plane. So, and carbon still has that empty p orbital that can donate to. Does this make sense? We just switched like where the pi bond was. Now the pi bond is between that carbon and nitrogen position. Technically, this is an amide structure. Instead of being in the carbonyl position with the carbon and the oxygen with the double bond. Is this making sense? You guys can stop me if you're like, oh, hey, I don't know what p orbitals are, because it's best you ask now before seeing this on the exam. Are we good?
I
Cool.
think so. Yeah.
All right.
I have a question about
I can't hear you. You're breaking up a little. Can you repeat that?
I have one question about hybridization. So
Mhm.
do the same rules that apply to any other is that you just look at the steric number and see hybridization it is?
So you look at the steric number and then you look if it has resonance. If it has resonance, it's more likely to be the less steric number, if that makes sense. Like it's more likely to be sp2 in this case versus what would it have been if it was just this structure? If it was just this structure, what would it have been?
S3.
Yes, correct. This would have been sp3, right? But because, for example, just as I'm drawing it here, it's sp2, this would be the more, like if you're asked what's the hybridization on this nitrogen or on this atom, you're going to be like, oh, it's not sp3, it's actually sp2. You see what I'm saying?
So even if it's not quote unquote done as sp2, it would still be considered because of the
Yes.
possibility of resonance.
Yes, and that's the point here, is that sp3, sp2, sp, they're all fluid structures. It's just the theory to justify bond angles. So we're justifying a 120 bond angle here versus a 109 bond angle here.
Okay.
Do you see what I'm
Thank
saying?
you.
Like we're basing the answer on the more probable bond angle, which in like resonance and in chemistry, we'll notice that it's not actually just as easy as counting the, steric groups or the Vesper groups or electron groups, whatever term you learned. It's based on what's going to make more sense based on resonance, based on aromaticity, based on allylic, factors. But yeah, that also I feel kind of answers the next question. So we're going to move on and do 2.76. In the compound below, identify all carbons that are electron deficient and all carbons that are electron rich. Justify your answer with resonance. So this makes it much easier. All right. Out of this pi bond, all these pi bonds, there's going to be one carbon that has a little bit more electrons versus one that has a little bit less electrons. Can we see the resonance happening, whether we go left or right? So if we decide to push this pi bond up, I just stated this in the previous question, that carbonyl carbon is a little electron poor, right? It's less likely to have electrons, especially in the first resonance case, if I'm just moving that pi bond up. Yes? No? Maybe so?
Yeah.
Yes. See that? Okay. And now if I decided to, because that would have been a positive charge, I decided to push, you could push here first, but then you would have to push here. Okay. I'm skipping that intermediate resonance structure and I'm just pushing that pi bond here. Okay, now can we agree that there's a slightly more positive charge on this carbon now?
Yes.
Okay. And same thing can happen if I decide to first push this here, or rather just push it across because there would be a carbocation here. Now, where is the electrophilic position? That would be slightly here, right? Yes.
Yes. At the
Yes, okay.
carbon, right?
Yes. And then the last resonance structure would be with the lone pair on the oxygen forming a carbonyl on the right side. Does that make sense? And so the opposite is true for the electron rich. And I mean, you guys can do this on your own, but try practicing all these resonance structures and see where it's most likely for a carbon to be in a more electrophilic. It's going to have less electron density because it's that pi bond is being taken away from it, essentially. These are just like skill builder questions. This is the same thing. I want to move on to like a little bit harder resonance questions. These are all going to be resonance questions. I also have some from the exam on here, I think. Yeah. Cool. Okay. So let's move on to these resonance questions because I feel like they're a little bit better. All right. Did anybody do this already? Where is my resonance? What would be the most contributing? Which pi bond is pushing up?
The pi
Or
bond
pushing
would go
down?
to the oxygen, will push up.
Yes. Pushes up. Oxygen would be negative. And then you have your positive charge here. And then this, right? Yes, correct? You would end up with a positive charge on the nitrogen. I can draw this for you. Correct? But why couldn't I have pushed the pi bonds on the right side? Could I? Yes, no, maybe.
Is it because of the octet rule?
Yes, octet row, you would have to get rid of this hydrogen. That's not possible. This is if it was placed here, it could be, and pretend like that this pi bond wasn't there. We could have this pushed up and then pushed here, right? But because that carbon already has 4 groups, that wouldn't be possible. So yes. Okay. Is this the same one? All right, I just kind of gave away the answer. All right, what about here?
Would the pi bond inside the ring move to the right
Towards the
and
oxygen. Wait,
huh?
towards the right? Did you mean this way or did you mean to the
Oh no,
left?
yeah, the left, I'm sorry. The
Yeah,
left, and then the pi bond on the oxygen would move up.
yeah, exactly. You see, you guys are starting to get it right now. Like it's shouldn't be that bad. All right, well, what about this nitrogen? It
Wait, I have a
has a
question
lone
though.
pair.
Why isn't it ideal to move it to the right? I'm just like, I understand this is correct and why, but I just want to know why isn't the other way correct?
Because you have a hydrogen here, and as the previous person just stated, carbon
Oh
already
yeah,
has 4 groups.
I keep forgetting the imaginary hydrogens.
Yeah, always remember the imaginary hydrogens. Carbon has to have 4 groups. There's no such thing as a 5 bonded carbon. Well, no, it's only in transition states. There's no such thing as a 5 bonded carbon. So if you draw 5 bonded carbons, you know you did something wrong. Okay, so yeah, you would push that pi bond to the left. All right, but what about this nitrogen? Anyway, can you tell me the hybridization state on this nitrogen and whether that lone pair would be localized, delocalized, and bond angle?
It's sp2 and delocalized.
Hold on.
And
Why do you say
yeah.
that? Why is it sp2?
Because
Where
it
would
has
you be
resonance.
donating? Would you be donating here?
Yeah.
How? This carbon already has 4 groups. Even if I drew it the other way, humor me. Even if I drew this the other way. Like that positive charge here now. Can that lone pair donate?
No, because it exceeds the octet rule.
Yeah. Nitrogen, oxygen, and fluorine are the only ones that always have to obey the octet rule. Carbon is usually going to obey the octet rule, but even if it didn't, like this is not possible. There's no more. Carbon has a like set size on p density, so it wouldn't be able to hold that extra lone pair. Nor would it be a good idea to push that pi bond up to oxygen and form like a double negative charge. So yeah, that actually would stay as sp3.
I have a question, and I know you touched on
Yes.
this like in previous questions, but I think the person answered that it's sp2, if I'm not mistaken, or did I hear wrong? If yes,
Yes.
how is it
They
sp?
asked.
How is it
It's
sp2 instead of 3? I don't like I don't understand
it's
the concept of it.
it's only it's not sp2. It's sp3.
Oh, okay. Thank you. Okay.
Yeah. Did that make sense?
Yeah, because I thought he said sp2, and I was just like very confused.
It did say
No.
sp2 because I thought it could be delocalized, and it would be sp2 if it could be delocalized, right?
Right. Correct. But it's not. You see how there's slightly different cases where in the first example or the second example we saw in resonance, that nitrogen could donate. Remember, because it was right next to carbonyl. But in this case, it can't. So keep that in mind.
I have a question. Like if
Sure.
it is if it is sp3, so I think the lone pair is not count into the steric number, right?
No, it is counting into the steric number.
Oh,
We're
okay.
counting 1, 2, 3, 4
Ah.
groups.
All right, thank you.
You're welcome. All right, what's happening? Talk to me.
So like the thing will go to the
You get a primary carbocation, that's unstable. It's like very unstable. We don't want primary carbocations.
so you move it.
It's very unstable. This is so unstable that this wouldn't exist. You know, you would have to like have a very low like temperature, but most
So-
likely
so we
you would
can-
have. Sorry,
We can
go
move
ahead.
that pi bond over, right? The one that's on the right
Hell
side.
yeah, we can. Hell
All
yeah,
right,
we
cool.
can.
And then we'd also move the other pi bond over too, right?
All right, but let's see if what your idea works.
No, wait,
Based
that
on
wouldn't
what-
work because then we'd have a carbocation on the left side.
Yes, sir. Right. That's what you're suggesting.
That's what I did
Right.
at first before I corrected myself. Yeah.
Yeah. Don't want carbocations, or primary carbocations. Tertiary carbocations are fine. Resonance stabilized carbocations are fine. And allylic carbocations are fine. But you don't want a primary carbocation. You would get something called a hydride shift. Something called a hydride shift before you get a primary carbocation. And then now this, because this has two hydrogens right now, we all can see that this only has two hydrogens, right? That's implied because of the positive charge. Most likely there would be a hydride shift from this position there, and then you would end up getting a positive charge here. This is going to be important because you guys are going to start moving fast. I'm just introducing these concepts a little early so you can start thinking like, oh, okay, I'm starting to get the picture. I'm starting to smell the hydride shift. So yeah, this wouldn't work. It is a resonance structure, but say no bueno carbocation.
I have a question.
Yes, go ahead.
So in problems like these, the goal is to build a resonance structure that gets rid of the carbocation, right?
You won't get rid of the carbocation because you don't have enough electrons. We're not doing any reactions as of right now. So what you end up actually doing is there's a conservation of charge and resonance. So whatever you started with, you can, like in the previous question, we did like a positive and negative example, or maybe I erased it. Or here where we decided like, oh, if we went to the other side, we would form a positive oxygen and a negative carbon. It's still a neutral charge because 1 plus and 1 minus cancels out, and it's still going to have a conservation of charge. Do you see what I'm saying? Like you can, it's slightly different because I also forgot to add the positive charge here when I pushed everything. But there's always going to be a negative or a negative and a positive or a neutral. It's just always going to conserve its charge. Its overall charge, it's going to still be positive. So the overall dominating or most contributing resonance hybrid structure is still going to have a positive charge. Unless it started off with a positive charge and a negative charge and you got rid of it. But yeah, I mean, sorry, this is a long-winded way of saying yes and no. If it has a positive charge and you can get rid of it by forming a positive charge on a more stable atom, yes. Or if it has a positive and negative charge and you're going to neutral, yes. Or if you had a neutral molecule and then you went from a positive and negative charge, but that positive and negative are on like a nitrogen and an oxygen and they're more stable, then yes. But yeah, okay, so the positive charge is still going to be there on this structure. So that
Okay.
should give you a hint too.
Yeah,
Sorry.
thank you.
All right, so we push
So
the first
there-
pi bond. We know that the left pi bond doesn't get pushed. So if we had this structure, this is now a tertiary carbocation, right? This is extremely stable. But what's even more stable?
Could you delocalize lone pair from the oxygen?
Yes, and that's what we do. and we form a carbonyl. And this hydrogen, I'm drawing it like this to emphasize what's going to happen probably in your chemistry course is that eventually this hydrogen would be deprotonated by some kind of reaction. And then oxygen would gain these 2 electrons between the covalent bond or the hydrogen bond between oxygen and hydrogen. So, but yes, that is correct. And guess what? We made more pi bonds, and we also placed the charge on the more stable atom, on oxygen rather than carbon. Cool?
Can I ask you a quick question really quickly?
Sure.
Isn't oxygen more electronegative? Wouldn't you want a negative charge on it?
Yes, it is. And here's the point. That's a great observation versus carbon, right? But it's more polarized. Its electron cloud is slightly bigger.
Okay, got it. Thank you.
Yeah. And it would be not only because it's slightly bigger, but because it's you're going from a primary carbocation to a positively charged, not a carbocation, but this is technically would be considered like a kind of high alkoxide ion, where the positive charge is on the oxygen. It would be a positively charged alkoxide ion. Those are possible. But it's just more stable. It has more room. Cool. All right. PKs. REO. All right, let's talk about it. All right, what do we see here? Which one's more stronger base? Okay, cool. Stronger base. I was gonna view this question as what I like a little bit better for you guys to ask because it's the same thing. It's like the reverse logic. There's 3 hydrogens here, right? But we're only talking about one, the one in red. And technically there's 2 hydrogens here, right? But let's only talk about the one again in red. Out of these 2 hydrogens, which one's the more acidic hydrogen? A or B?
Is it B?
Okay, one
Is it going
person's
to
for
be A because of the orbital?
I want to take it like a quick poll. We have one
Okay.
for A, one for B.
I
Alright.
think it's B.
B. Anybody else?
I think it's A.
A. Anybody else?
A.
A. Okay, cool. Are we done with the voting? Are you guys still awake? All right. It is A, by the way. And the reason for that, think about the lesson we were just talking about, resonance, right? Which one has more resonance? If chemistry is going to go fast. So if I have some kind of base and I'm deprotonating this hydrogen, that's what ends up with the negative charge as they drew it originally in the first question, right? Looks like this. And tell me not that I could go and do resonance on the left side or in pink going to resonance on the right side. Versus if I was to depronate this hydrogen with the same nucleophile source with the same base, and you have this donate essentially, and there's only one resonance. So what I'm trying to show is that there's only one resonance structure that you can do here. Push this, make a pi bond here, and then make an alkoxide ion. This is what I mean when I draw an alkoxide ion. This is the alkoxide. But you only have one resonance structure, right? Here, in terms, you have 2 resonance structures that you can do, or 2 pathways to stabilize that negative charge. Okay, so we know if something is more acidic, the opposite is going to be like strong acid, weak conjugate base. This is essentially saying like which one has the stronger conjugate base. You see why I asked you like the reverse logic? Which one is more acidic such that their conjugate base is going to be weaker, because the more weaker acid is going to have a stronger conjugate base, right? Yes, no, maybe so.
Mhm.
Does that make sense? Can we?
Yes.
Yes. So what's the
So
answer?
could we just go by that logic where if it's a strong acid, then it'll have a weak conjugate base. So it can't be the right one because that's a strong acid. Therefore, it will be a weaker conjugate
No,
base.
no, 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 no. The right one is not the stronger acid. It's A
Oh,
is the stronger acid.
So if A is the stronger base or stronger acid, then B must be the stronger base.
Yes.
oh, okay.
So you're close. Just that's why, which one is more acidic. You can go based on that. Chapter 7 is going to really illustrate like stability. But for now, yes, whatever is the stronger acid. So now this base is more stable. This base would have been more stable. This base here is a much more stable base, and stable bases are weaker bases.
So the stronger bases have more resonance compared to the stronger acids, if I'm not mistaken.
I think you're saying things a little bit differently. So the more stable base is the one that's going to have more resonance, and that's going to be a weaker base. Right? Do you see what I'm going with this? Like it's only a strong base because it's unstable and it really needs to pick up that hydrogen.
Okay, yeah, I understand now.
Okay. Are we good? Can I move on? Yes? Okay. For each pair of compounds, predict which one is more acidic. Explain your choice. Why? You guys have pKa tables. Yeah, let's see. I mean, I don't know if you guys want to do breakout rooms. Let me see. 20. This would be a breakout room, but it doesn't matter. You guys want to do breakout rooms to do like answer the next 2 questions?
No, not really.
Not really. Okay, cool. All right. Let me see how much we have left. Do you guys want to move to like test questions or finish like all of these?
Test
Do
questions.
you guys want to just say just go to exam questions? Because I feel like some of this stuff is kind of like boring, but you guys have to know all of it. And these were the ones in your PowerPoint. Are we good with naming, by the way? Because I would love to get into some questions as well. But are we good with naming so I can go to like the test questions?
Could we do a few naming ones? Just
Sure.
like a handful.
Sure. All right. Let's start it off like right off the bat. All right. What kind of yeah, and this is like a hard example, but like who cares? You're gonna get a bicyclo anyways. So give me a bicyclo practice question. Where would I start? How would I start doing this?
Would the parent be the ring?
Yeah, the bicycle thing.
Well, which one?
Both.
Both.
They're both, right? We
Yeah, both.
automatically know it's bicyclo. It's bicyclo something, right? How many carbons do you have in
8.
your bicyclo? 1, 2, 3, 4, 5, 6, 7, 8, right? So what is that? What's the
Octane.
prefix?
Octane.
Octane, right? We're almost there. We start at the bridgehead carbons. Where are our bridgehead carbons?
Where the hexagon and the square meet.
Okay. And which way am I counting? Am I counting up, to the right,
Bottom
left?
bottom left.
Bottom left. Why?
Because you have to go around the longer
substrate
spot first. Oh, sorry.
Both of you guys are right. Right? So 1, 2, 3, 4, 5, 6, 7, 8. Right?
Yes.
What are these groups called?
Methyl.
Actually, they're all the same groups. This would be 2, 2, right? This would be 5, and this would be 7 methyl. Okay.
I'm sorry.
Type it in
Can
the
you
chat, put
please
it together.
explain one more time why we didn't start at 8 instead of we started at like the position we started?
You go the longest route, the longest carbons. So here you can tell there's 4 carbons on the side. Here you can tell there's 2 carbons on the side. And is this a pathway between 1 and 6? If I was to draw this differently, this would be like first pathway, second pathway, and then third pathway. And we just go based on the one that has the most carbons. This side had 4 carbons, this side had 2 carbons, 2 carbons, and this side had 0 carbons. Does that make sense?
Yeah.
Okay. So somebody type the name of this bicycle in the chat, since we now have identified the longest pathway, this smallest locant, and the parent chain. And actually, I have to check the chat. I don't know. Is anybody running? Or just tell me what it is. You can unmute yourselves.
Is it 2, 2, 5, 7 tetramethyl bicyclo 4, 2, 0 octane?
Can you repeat that? So I'm just gonna move this. Okay, say it one more time.
2, 2, 5, 7 tetramethyl bicyclo 4, 2, 0 octane.
Yeah.
Do we agree?
Yes.
Okay, good job. Do you guys
Can you
want another
explain
naming example?
I'm sorry, can you explain the 3 numbers in the middle, bicyclo
Those
and
are the pathways. So whatever pathway I get, let me just draw another example. So whatever pathway I get, let's draw this one like this, maybe. Okay, that's a terrible bicyclo. Okay, actually, let's make that just 1 carbon. So here, same example, starting at the bridgehead carbons, we're going to our right, correct? And here I'm not putting any like substituents on it, because I just want to show you like the example. So here on this side, we have 3 carbons in our longest pathway. 2, 3, 4, 5. What's the next pathway? It would be this way. 6, 7. This is 8. This is also an octane. But in this case, we would be naming this octane 3, 2, 1 octane, right? Bicyclooctane. Do we see why? Because there's 3 carbons here. There's 3 carbons here. There's 2 carbons here, and there's just 1 carbon here.
Oh, okay. All right, I
Okay.
get it. Yeah,
It's
thank
from the
you.
bridgehead carbons. Okay.
All right, thank you.
Sometimes you don't even have to include the 0, but that's just, it's best that you probably should. Newman projections, are we good? Do we understand? Did Eric tell you to buy a molecular modeling kit, or did he show you a molecular modeling kit in class? I believe
Yeah.
he did.
Mhm.
Okay. It's cheap. You can get it from the like science library as well. So just so you know, but I think we should practice some of those. But I can just move on to some, some fun test questions. Just for kicks and gigs. Pick. Do you want 2021 or 2021? Okay, fall or spring? You guys feeling springy or fally?
Spring.
Yeah.
Spring. All right. Spring. Spring it is. Okay. Functional groups. Let's bang out this exam. Give me some functional groups. Yell them out.
A ketone, the first one.
Ketone. Yep. Ketone. Do we see another ketone? Don't be shy. This is the time to get it wrong.
Ether or ester?
Ether ester. Tell me where the ether. Is it here or is it here?
I'm
There's
not
a
seeing
chart
anything
in your
you're
book.
drawing. I don't know if it's just me.
Does
I
anybody
can't see
else
anything
what I'm-
either.
Oh,
No.
really? What the hell?
Yeah, I
Right
think ever
bottom.
since like that black thing came up, we can't see anything. It's a little blurry.
Oh, really? Hold on. My computer is like freezing a little. Connection a little bad. I'm getting the pinwheel. I'm sorry, guys. Hold on. Give it 1 second, because now it's further.
Now I see your that drawings.
Oh, okay. Hold on. Mm, 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 mm. Mm. Okay. Now? Wait, no. Now? Did it work?
Yeah.
Yes.
Okay. Did you see, okay, ether here? Yes,
Yes.
working. Okay, cool. Sorry. I had too many apps open and then it freezes. Okay, ether. What about this side? What's B?
Ester.
Esther.
And the
Okay,
bottom, amide.
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 Yes.
What about this group?
Alkyne.
Excuse me?
Alkyne.
No, it's not an alkyne.
It's not.
Is that a nitro? Nitrile.
Nitro. And we're gonna write these differently just so you guys know, to throw you off, because we're bored. So we might write it like this, okay? Just BT dubs. Also, if let's say I had an aldehyde here instead of an ether, let's say I decided to draw this an aldehyde, right? I could have also easily drawn this like this, CHO, and this is an aldehyde. So don't let those things confuse you. The condensed form is also fair game. So whether that be COOH, which is a what? What is that? What kind of group is that? Anybody?
Aldehyde?
No. We just said aldehyde would be the CHO.
Carboxylic acid.
Yes. Good job. Carboxylic acid. Okay.
Oh, oops.
It's just the condensed form of it. It's like it's molecular formula, but in the condensed form. And I'm not showing you the double bonds. That's the important part. Don't confuse this for like an alcohol or something. I'll be like, oh, there's a carbon here, and then there's an like OH here. No, I'm telling you, there's only one hydrogen. So if there's only one hydrogen in a carbon, it has to be a carbon double bonded to an oxygen and a hydrogen. Okay? Cool. All right. So what were we talking about earlier? Is there resonance? Will there be resonance? Is this delocalized? Is this not delocalized? Give me some angles. What's possible? Talk to me. Give me the hybridization geometry and bond angle on this nitrogen.
We need the steric number, right? First and foremost.
Yeah, I mean, you can figure that out. What's the steric number? Or what do you think the steric number is?
4.
3.
4. Okay. Who said 3?
I did. Isn't it 2 lone pairs and
Why?
then like
It's
one
not 2
lone
lone
pair
pairs.
and
It's
then
one lone
2
pair.
bond?
Okay, yeah. So you're automatically going to the resonance, right? Assuming so.
Uh,
Because as
I
it stands, it's SP3 right now. But why would it be SP2? Or do you think it's SP2?
Because of resonance.
Yeah. So where's the resonance going? How are we making this resonance? Look at your carbons adjacent to the nitrogen. Are those sp2 carbons?
Would the carbon become a carbocation?
Yes. Carboanion. Carboanion. The cat is for the positive charge.
Yeah,
Yes.
carboanion, yeah.
What's happening in reality is that there's a pi bond here. So this pi bond here is going to be donating to this carbon, right? And it does so because since it's sp2, there's space for it in this p orbital, right? And now you have this empty p orbital that can take up this double bond that's going to be formed when nitrogen donates that lone pair.
The original
starting to make
structure
sense?
is more stable though, right?
No, I mean, yes and no. Like the point is, it's like, yes, if you just look at this, it's like sp3, right? 109, right? Tetrahedral. but the point of this question is not to test you on the original parent structure. It's to see if you actually get that this has resonance and that this would now be what?
SP2?
Yes.
But it still has 4 bonds.
No, but this is considered that pi bond is considered one group, one steric group, or
Oh,
one
yeah.
Vesper group.
Yeah, you're right. Also, I have a question. You know how you move the 2 electrons on the carbon? Wouldn't that exceed the octet rule? That's my whole confusion when it comes to like moving the bonds. You never know because originally there's a hydrogen there which fulfills the octet rule. So
No,
once
it
you move
doesn't.
that pi bond,
Okay, so hold on. Just to ask you, how many if this had so it's 1, 2, 3, 4, 5, 6, 7, 8. Is it breaking the octet rule? No, it's the formal charge is now negative.
okay. Okay,
Do you
yeah,
see
I
that?
see.
Do
I
you
see.
see a carbon? So carbon, hydrogen, like just in theory, is that breaking the octet rule?
No,
No, right? But what's the formal charge on that?
-1.
Yes, exactly. So to answer your question, it's not breaking the octet rule. And carbon technically can break the octet rule. The only ones that can't break the octet rule are nitrogen, oxygen, and fluorine. And mostly we're just going to be talking about nitrogen and oxygen. Okay. Good stuff. Okay, moving on. P1C. What is this? Is this SP2, SP3, SP? What's the shape? Oh, and did anybody answer the shape for this question? What's the shape now? And what's the bond angle?
Trigonoplanar 120.
Yes.
You know like how for tetrahedral there's 3 different angles, 109, 107, and 105. How do we know which one to look out for?
109.
Oh, okay.
109. You
Okay.
look out for 109. You could technically, like if you had SP3 with like a lone pair, you could be like less than 109, but it's whatever. You could just put 109. Or if you want to be like really nice about it, put less than 109. All right,
To
next
find the
question.
bond angle, what are we looking at?
Bond angle, you're looking at the geometry. Like
for these
there's no
questions,
way
you
of
always want us.
go ahead.
Sorry. So for this question, you always want us to find the resonance and then answer the questions based on that resonance figure that we found.
Yes. Is there resonance? Can you smell the resonance? I'll give you a hint, like an Orgo 1, like what is Orgo 1 without resonance? Like if there is resonance, there will be resonance.
There is resonance. You
Yeah,
can form a pi bond with the negative charge.
can you form a pi bond with this negative charge? I
Well,
mean,
with the
maybe you
lone
can.
with the lone
No.
pair.
Yeah, I mean, yes and
No,
no.
because the
Okay, who says no?
hydrogens. The
Yes,
hydrogens.
thank you. Thank you. Good stuff, whoever said that. There's hydrogens here, right? What if I did this? What would happen there? I'd have
Exceed
to
the
kick out a
octet.
hydrogen. There you go. I would like have to kick out a hydrogen for that to be possible. Say correct, right? Does that make sense?
Yes.
Yes. So this would be like an unstable carboanion. But there's nothing to stabilize it. Yes?
Yeah.
Yes.
Okay, good. So what are we, so it's not SP2 and it wouldn't be SP2. What is it?
It's SP3.
Okay, what's the shape?
Tetrahedral.
Trigonal pyramidal.
Yes.
Yeah,
Because
pyramidal.
lone pair. Think of the lone pair on there. Pyramidal, something like that. And what's the bond angle? Because of the lone pair. Because this is essentially like, if you're seeing it like this, whatever, methyl group, methyl group, methyl group, carbon, lone pair. This is why we say less than, because this lone pair is pushing on these methyl groups. Its electron cloud is going to be a little bit bigger. That's why we say less than 109 or 105. Cool? Easy?
Yeah.
Yes? No? Okay. All right. Test questions that are, this is how we're going to test you on resonance. Let me see how many I have. Yes, exactly. This is how we're going to test you on resonance. So talk to me. What does this look like? Why are we pushing these pi bonds, these electrons? What's going on? Where are we going? Are we going left to right, right to left? We're going to stabilize that secondary carbocation. What kind of pi bond? Going the pi bond to the right or the pi bond to the left? Guys, talk to me. Is it this pi bond or this pi bond that's moving?
Is it the second one? We're trying to get the positive charge to the nitrogen.
Yes, because if we did this, what would we have formed?
Carbocation.
Yes, but no, be more specific. What kind of unstable carbocation?
First degree.
Yes, you would have a primary or first degree. We call those primary carbocations. So we don't want to go there. I mean, if you wanted to, you could draw that resonance structure, but I'm going to tell you that that's not the major or most contributing. So we have to go this way, right? Does that make sense? So just for kicks and gigs, let's draw this. Okay, now where is the positive charge? Where's the positive charge?
On the carbon to the right of the nitrogen.
Yes. And now having that in mind, what could we do? Is there more resonance to be had?
Yes, the lone pair from the nitrogen can form a pi bond with that carbon.
Yes. And now we get that. Am I missing a charge? Say yes.
Positive charge on nitrogen.
Yes, thank you. Conservation of charge. Boom. So which one's most contributing? Or major product? This one, right? Positive charge on nitrogen.
But aren't we
Cool.
looking for a negative charge on the most electronegative?
Yeah, but there is no negative charge in the original structure.
Oh, okay. So it doesn't matter. It could be negative or positive as long as it's on the most electronegative.
Yes, yes, ma'am. Okay, next one. We have a positive charge. What are we moving? We have several options. What do you think? So lone pair on the oxygen, right? 2 lone pairs. We could go here or we could go here, right? What do you guys want to do first? Left side? Cool. We could do this, right? Positive charge, but then that's pretty much it. I can't do much else, right?
Right.
Right? But now let's say I wanted to go, like if this was the A route, what about if I did the B route? Right? So now the pi bond is here. Wait, oh, that's right. Pi bond is here. Okay, positive charge. Where? What kind of position is the positive charge? First degree, second degree, third degree. Is it primary
Third?
carbo? What kind of carbocation is being formed? Is it primary, secondary, or tertiary?
Tertiary?
Tertiary. Right? Now where am I going? What 2 options do I have? Do I have another path?
Oxygen
Would I
pi
push
bond?
this one or this pi bond?
Oxygen?
You want to go this way? Right?
Yeah.
Okay. Was there another path that we could have taken?
You could have gone to the nitrogen.
Yeah, and is this a better path? Would this have been
No.
I want?
No.
Why? No,
Oxygen
because
is
why?
more electronegative.
Yeah, but this is a positive charge, right?
Oh, so it would be better.
I'm asking you. What
But by the
makes more
same logic,
sense?
wouldn't it be better for it to be on a carbon?
Yes, but carbon doesn't have the same like polarizability nor the same p density. It's slightly bigger. Like carbon is designed to have 4 groups covalently bonding to it. At least nitrogen has like an unhybridized p orbital, and oxygen would have 2 unhybridized p orbitals that it can kind of play with. I know your logic seems, and don't get me wrong, that's exactly how I was thinking first time around. But this is more stable because you'll learn that nitrogen is the better pi donor as compared to oxygen and as compared to carbon. So what I'm trying to say is that these 2 structures, this one and this one, are less contributing than the pi bond or the positive charge being on nitrogen. It's less electronegative than oxygen. Yes, that is true. So it's less likely to pull those electrons, but it's more polarizable. It has an unhybridized p orbital that can donate better than carbon. Carbon is going to be unlikely or less likely to have a positive charge if you're comparing positive charge on carbon or nitrogen. Yes? No? I mean, we could keep doing more examples and hopefully.
So the 2 oxygen resonance structures are equal to each other?
Yes, essentially. But all you have to look is like for the most or major contributing. Good?
Yes.
Okay, moving on. All right. What does this look like? All right. Oh, how would I find this out? This is tricky. Do you know what a constitutional isomer is?
Yeah, same molecular formula, but different structure. Would
Yeah.
you try to use nomenclature?
Nomenclature takes too long. So how would you do this?
Only one of them doesn't have or it has an sp orbital instead of a sp2.
Nope, doesn't matter. That's not the easiest way of going about this.
Counting the carbons?
Yeah. Oh, counting the carbons and or atoms. So whatever the molecular formula is, you'll be able to like understand, okay, this is not a constitutional isomer. This is a completely different compound. So you want to see which one is essentially different from the other. And you will be able to like right off the bat, they all have Br. So we know that they all have Br. We can count the carbons, but let's see, 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6. They all have 6 carbons as well.
If
So-
you're writing on the thing, we can't see it, I don't think. Mine's is still
Oh, I
black.
didn't. I mean, like, I kind of just pointed at it. Is there a laser one for this? I think there's a laser.
Yeah.
Oh, yeah, there's a laser. So I was just pointing.
Oh, okay.
Is this pointing? Yeah. Okay. So I was pointing 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6. So they all have 6 carbons. But they may differ in hydrogens. So if I'm looking at hydrogens, how many hydrogens do I have? This is counting implicit hydrogens. So I have an implicit hydrogen here, I have 2 here, I have 2 here, and in all of these, since they're also connected to 2 carbons, you have 2 hydrogens here.
I don't know where they at.
Oh, start looking.
What do you mean start looking?
Guys, turn off your mic, please.
Yeah, please. Thank you. Okay, so different hydrogens, different compound. How many hydrogens are on Roman numeral 2?
None.
On Roman numeral 2, there's no hydrogens?
No, I meant on the carbon, like on the first carbon, there's none.
Oh, yeah, 0. What about the second carbon?
Also 0.
Yes. Third?
The third one has 3 carbons. That's the one on the like top, not where they all meet.
This one? No.
No,
Where I'm
the
That
saying-
has
top.
0.
0, correct. So this one has 3?
Should be 9 carbons, right?
Yeah. Do you see a pattern here?
Yeah.
The ones at the end, terminal carbons, have 3 hydrogens, right? Unless stated otherwise. That has 9. We had a 9 in the original. 9 hydrogens here, 9 hydrogens here, right? What about in the third one?
You have 9.
In the third one, let's count them. 3
You
here,
have 10?
2 here, 1 here, 2 here, 1 here, and there's 2 here. How many is that?
10.
5, 6, 8. Is that 10, buddy? 3, 5,
It's 11.
6, 8, 9, and 11. Whoever said 11, you are correct. This is 11 hydrogens. 2 hydrogens. 11 hydrogens. I don't even have to go any further because I know that since this one doesn't have the same amount of hydrogens as the first 2, it's very unlikely that these also have 11 hydrogens or a different number. You're only going to have one multiple choice answer. So since this has C11, like so C6, H11, Br1, we know that this is not a constitutional isomer. And just to prove my point, like I can count the rest of them. Hydrogen here, There's no hydrogens there, but there's 2, 2, 2, 2. That's 9 hydrogens as well. There's 3 here, 2 here, 1 here, 3 here. So that's 6, 9 as well. Does that make sense? Do I have to draw
Yeah.
all these hydrogens? No? Okay, cool. Can we move on?
Is this like a typical question that'll be on the exam?
Yeah. These exams are basically something, a similar version of what's going to be in your exam. You're going to be asked resonance, you're going to be asked REO, you're going to be asked naming, you're going to be asked Newman, you're going to be asked chair, and yeah, different variations of these
Boiling point?
questions. Boiling point, yes, thank you. Boiling point, and that's pretty much it. So resonance, nomenclature, boiling point, REO, Newman, chair, and that's it. I mean, it's not going to be that tough. I mean, first exam, well, we'll see. We'll see. We'll see if it's that tough. I'm going to make it an exam review. Again, we'll do like the second one. We'll do fall. If we did spring today, I'll finish fall tomorrow or Sunday. But definitely study those 5 topics. Rank the following and increasing boiling point. All right, what did Eric tell you? Branching, right? It has something to do with branching, correct? And
Yeah.
intermolecular forces, correct? And inductive effects, or like, heteroatoms, yes? So
Yeah.
based on this, is there anyone that we know that's gonna be pretty low on the boiling point measure? Based on like
What?
molecular weight? Yeah, okay, so good observation. But I want you to just quickly, how many carbons are here versus, and maybe I should give these names. A, B, C, D. So how many carbons are in D versus how many carbons are in F?
There's
There are
5
5 carbons in D and only 4 in F.
Yes, and so based on that, I know that it's branching, but can we see which one is going to have the like
Yeah,
based
F
on,
will have the lowest because it has the lowest carbons.
so F, yes, correct. And this would be 2. All right, good. What about the next one? Does C have the same amount of carbons as D?
Yes.
But it's less branch, correct? Because here we have basically like all these methyl groups are on the same carbon, versus here it's a little bit more linear. There, like the packing effect of the like lattice structure or the allotrope is a little bit easier. So what about in 3? Or sorry, I gave it away. So C is 3, correct? Do we get that? Yes?
Wouldn't
No?
Can you zoom out? We can't see the whole thing. Wouldn't A be next because it has less carbons? It only has 3 carbons compared to C.
Yeah, but it has these big electron groups, electron withdrawing groups or heteroatoms that are on there.
Oh, okay.
That's going to increase the molecular weight of this compound, is it not? If you compare chlorine to carbon.
Yeah.
Yeah. Okay. So here, if I was comparing this to another 5 bonded carbon, 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. Which one would have the higher boiling point? C or imaginary X?
Imaginary
Imaginary.
X.
Yeah, good job. Okay, that's just the point that I'm trying to lay out here. All right, 3. What about between A and B? What does B look like? Can anybody draw B? Do you know what this looks like?
They're all
Carbon in the middle,
All right.
chlorides at the outer ends.
Yeah. Okay. So which one has the higher boiling point?
B.
B Compared to A, yes. So B would be 5, A would be 4. All right, and that just leaves E as 6. But also, it's because it has what intermolecular phenomenon?
Hydrogen bonding.
Yes, ma'am. Okay. All right, draw the Newman projection. All right. To the wolves. What does this look like? This is the only reason why I think naming is important, but naming is like a less useful skill. So how am I drawing this? I have 2-methyl 3,4-diethyl hexane. What's my parent chain going to look like? How many carbons?
Yes, 6 carbons.
Thank you. 6 carbons. Let's draw them. 1, 2, 3, 4, 5. 1, 2, 3, 4, 5, 6. All right. We said 2-methyl, right? 2-methyl. What else? 3,4-diethyl. Boom. Draw it with a little bit of angle. Boom. Boom. And is that it? I feel like that's it, right? Hexane. We counted 6. We have 6 in our longest parent chain. This is our 3 and 4 ethyl, and this is our 2-methyl.
What does the dye indicate, please?
Dye indicate that there's 2 of them. One ethyl group at 3 and the other ethyl group at 4. So
But it's
since
diethylhexane. Okay, never mind.
this is the naming thing, so it would be 2-methyl. I forgot, we did a naming question before. This is what did we do? Like, whatever, we did a naming question where it was like 2, 5, 7. In the bicyclo example, that's where we did tetramethyl. That's where those prefixes are coming from. So since this is 4-methyl or 4-ethyl and 3-ethyl, when you write it, it's going to be 3,4-diethyl. Right? Okay, cool.
Yeah.
But we're not asking about naming. This is the only reason why you need to know naming is because you will get word problems and it will assume you know how to draw it. And we're assuming that you know how to draw it. So, okay. I can easily make this question a little bit harder, but I want to show you. I'll give you this example first, and then I'll tell you why the perspective matters. So the perspective here is telling you to go from C3 to C4. So since I'm telling you to go from C3 to C4, pretend like your little eye is right here, and you're viewing it this way, right? If you're viewing it that way, and I'm also not drawing the implicit hydrogens, I'm not giving it any stereochemistry, but you know that there's a hydrogen here at number 3, correct? We know that there's a hydrogen here at 3, correct? And we also know that there's a hydrogen back here at number 4, correct? That I'm not showing. But in this case, I'm looking almost like as if this was in 3D, like front facing. And so I'm front facing that molecule. I'm looking at it like this. Yeah, that's a terrible circle. I'm looking at it like this. What's on this position number over here on the top position?
The methyl.
What methyl? I'm looking at it from 3.
Is that going to be the isopropyl?
Yes, it will be the isopropyl. It's not a methyl because you're looking at it as if the front. So if I was to separate these two, let's just look at it as a front carbon. This is carbon number 3, the front carbon. What's on top is all of this shaded in pink. Right? So that is an isopropyl group. And you're right. I'm just gonna write it as isopro. That's the isopropyl group. Okay, what do I have to my left? I spy with my little eye. What's on my left?
Ethyl?
It could be ethyl, but it's technically, if you're viewing it this way, from this position,
The
this is
hydrogen?
your left, this is your right. Yes, yes, ma'am. And that on my right would be my ethyl. And now, what's like back here? What's back here? You know, I can't see it, but like you see something is back here. Oh, that's a beautiful circle. This is representing our back carbon. What's on our back carbon? What's to my left and what's to my right and what's pointing down or bottom?
Well, we have a hydrogen on the left.
Yes. To our right,
Ethyl?
yes. Pointing down,
Another ethyl.
yes. Perfect. Beautiful. Thank you. All right. Now, what would be most and least stable and why?
Anti,
Anti, right? So how would I do this?
you'd rotate it.
I'm gonna try to rotate it. Style, no, cut. That doesn't work. You guys are gonna make me draw this over again. Okay. Okay. So ethyl and isopropyl, we're just twisting it. Actually, let me keep the same original structure. Okay, let me just copy this. Duplicate. Oop. So I'm twisting it like 60 degrees to the left, just the back carbon. So if I twist it just a little bit, I'm gonna get the anti-configuration, right? Ah, Jesus. I'm gonna get the anti-configuration of these, where I have steric interactions with isopropyl and ethyl, hydrogen and ethyl and ethyl. And this is basically the angle between these two ethyl groups is essentially 0 degrees. This is most unstable. And most stable would be obviously our anti-position, basically what we drew first. Actually, what would be a little bit more stable is if we rotated this such that the hydrogen, I mean, this is kind of the same thing. Put hydrogen here, ethyl here, and ethyl here. This will be slightly more stable. But it's almost the same. It's just the hydrogen and the isopropyl are, this hydrogen is between isopropyl and ethyl instead of being between isopropyl and hydrogen. So it's a little bit better. But this would be our most stable. And this would be our least stable. Okay, but
For
we're gonna give
original,
you,
sorry.
go ahead. Keep
For the
talking.
original Newman projection, can you just highlight which ethyl how you get the ethyl, like which ethyl represent from the structure?
Okay, so here what I drew first was from before I twisted it. I had this structure, correct? I'm
Yeah.
going to draw this structure in green to represent this bond, essentially, this ethyl. What I'm saying, and I'll keep that one in red. I'm turning it this way, the back carbon this way, around, I don't know, X amount of degrees. Let's call it like 90 degrees. And now, since I'm rotating it clockwise, you get this ethyl group between isopropyl and hydrogen, this hydrogen between isopropyl and ethyl, which makes this whole structure a little bit more stable, and this ethyl group here. Does that make sense?
How about the front ethyl, the right?
You keep it the same. You keep it the same.
Oh, okay. Thank you.
Yeah. Yeah. Okay. The only thing with these kinds of questions is that this is perspective dependent. And what I mean by perspective dependent is that just as easily, the way we would make this question harder, we're giving you this exact same question, but we're going to change this from, I don't know, maybe not C4 to C3. I mean, but yeah, essentially I'm considering C4 to C3. And what I mean by that, it may not, like, we may not tell you it's C4 to C3, but we may tell you that now we're viewing it from this side, looking down at it. Do you see what I'm saying? And this is the hypothetical question that you guys will get is like, is the projection the same? Because now our Mercedes-Benz logo looks a little bit different. Now let me erase some of this. Or actually, let me just copy some of this and add a new page because this is getting too much. New page. And let's copy structure. Let's copy this structure. Copy. Okay. So in the first example, we're looking from the bottom, right? Now, let's see how this changes if we view it from the top. Oh, too much. Okay. How is this going to change? How is this Newton projection changing?
You're
Okay,
looking at
drawing my Mercedes-Benz logo. What's on my bottom? What's to the bottom that we
this
said was originally
carbon
red?
3.
No, look, we're viewing
Ethyl?
now the fourth carbon as a front carbon. Yes, it
Yeah.
is ethyl in red. Okay. Now what's on my left and what's on my right? I'm looking at front carbon as carbon number 4.
Left would be hydrogen.
What's on my left and what's on my right? Hydrogen's on my right or on my left?
Left.
Right?
Right.
I have left and right. Who's, is it here or is it here? What do you guys think?
Right.
Right? We have one answer for right. Anybody else
It's on the
agreeing with
left.
him?
Left.
Okay, I have 2 for left. Anybody else? No? Okay. It's on, yeah. Dude, you're right. It is on your right because originally it was on our left. That hydrogen was on our left. And more specifically, when you get a question like this, we may give you some stereochemistry. So if this was like a different group, let's call this, if this was a propyl group, we would draw this with a little bit of stereochemistry. With this, specifically telling you whether it's pointing up or down. And as such, you're gonna be, if you're viewing anything, think of like viewing your hand. If you're viewing your hand like straight at your palm, your pinky's on your left. But when you switch your palm around, now your pinky's on your right. Right? Like that's how we're viewing the perspective of like, oh, I'm looking at the molecule and I have originally hydrogen, my pinky to my left, but now I'm looking at my molecule from the backside. Hydrogen is going to be on my right. Okay. Look at your hand. If you don't have the molecule kit. So hydrogen's on my left. That green ethyl is going to be, or hydrogen's on my right. That green ethyl is going to be on my left. and whatever's in the back is essentially obeying the same rules. So we have the hydrogen that's still there as well. Okay, so is that hydrogen on the left or on the right? Now answer the question. Is that hydrogen on the right? Is that hydrogen on the left? Look at your hand. You guys still confused?
A little bit. I think Newman's projections are like the hardest topic.
Okay. We'll go over Newman projections more often.
How
or
important
once
is
before. Go ahead.
since you're finding the most stable figure, how important is it for left and right directions? Wouldn't it still be similar since you're finding the most stable and least stable?
It's yes, but here's the thing. It's just being able to understand where groups are on the carbon, like whether it's on carbon C3 or C4, and what groups are those. Because we can easily give you like which one of these questions is not this compound and give you the name of the compound and the molecular formula, and you would just be like, oh, well, okay, so I'm not asking you most or least stable, but now I'm asking you, okay, or take it a step further. I can integrate this question, say, okay, which one of these answer choices is most stable, but the actual compound. So I can give you two different perspectives. And the only difference is that I'm putting the two ethyl groups that are on carbon number 4, I'm putting those on carbon number 3. And I'm putting like two methyl groups or something else, or like an ethyl group. I'm not giving you an isopropyl group. I'm not making the same groups. So you have to distinguish between, is it on C3 or on C4? Am I viewing it from like looking down to up perspective or looking up to down perspective? And am I also looking for the most stable anti-eclipsed or Gauss position? Because these questions, I mean, you have the textbook. You can see how difficult some of these questions are. We won't go harder than the textbook. We'll be fair. But these are the questions that you're going to see is that, okay, Newman projection. Let's think of stability. Let's think of what's the most stable. Let's think of how it's actually viewed, because it's literally called a Newman projection. And then let's see if the question was like, which one of these compounds is this compound? Like, is 2-methyl-3,4-diethylhexane? You need to know how to name, and you need to know how to draw the perspective in the right like group orientation with two ethyls on the like left and right on the back carbon versus one ethyl being on carbon number 3 and one ethyl, or I don't know, like there's a different combination. But it's to say that you need to understand how to do every single step in these to be able to answer the question correctly. But that's why we only give you 5 topics. And we're telling you what topics those are. So I hope that answers your question.
So a question, if you're looking on the C2 to C3 direction, how would you describe the back? C3?
Oh, sorry, we never finished this. So in the back, on the right is the hydrogen, on the left is the ethyl, and on top is the isopropyl group. So like that's what I'm saying. This could be an answer choice, and it almost looked exactly like the other choice. Do you see what I'm saying? Like they almost looked identical. Yes.
Hey, not sure if you heard my question, but if you're looking on the C2 to C3 direction, how would you
Oh,
describe the back?
C2, C3. Okay.
Yeah.
Depends if you're looking at from C2 to C3 like this.
Yeah, just like
If you had an eyeball here. Okay, well, let's draw it. Now you would have carbon, and there's still a hydrogen here, right? I'm not drawing it, but it's still hydrogen here. So now you have a methyl group, a hydrogen group, another methyl group, and the back carbon would have hydrogen, would have an ethyl group, and then it would have this, it's kind of like an isopropyl, but it would have this 2-ethyl group on it. That's what's on the back carbon.
Wouldn't the hydrogen on the carbon 2 be on the left?
It just depends on whether we give you, wedge or dash. It doesn't really matter. I mean, I
That's
could have
dash
done
though, isn't it?
here, since they're 2 methyl groups, it doesn't really matter. But if I was to draw it like this, yeah. If I was to draw it like this, then it's a little bit more clearer that hydrogen's on the left. Oh, wait, yeah, sorry. You did point something out to me. Yes, sorry, hydrogen left here. But the way I drew it originally, it just depends on how you draw the implicit hydrogen. But you can notice it's going to be on the same carbon. We have 7 more minutes, so I'm going to run through an Orgo question because we have a lot more questions left. And I'll finish this exam and I'll finish the next exam on Sunday. Okay? Sound good? Yes? If you're
Yes.
still here,
Yeah.
anybody?
Yeah.
Okay. Quickly, 7 minutes because I gotta check out of this hotel room. So, check out at 12. That's why. Oreo, atom, resonance, induction effect, and orbital. Technically, you can remember it as cardio. Did Eric tell you cardio or Oreo?
Oreo only.
Cardio.
Is it
He mentioned Cario though.
Mario? Yeah.
Okay. The only reason why he probably mentioned cardio is this because it's obvious. This one's charge, which students forget of, and this is distance from induction effect. So if you remember induction effect, just look at how many carbons away is it. So if we're going from increasing acidity, do we have hydrogen bonding? Do we have inducting effects? Which one doesn't have hydrogen bonding or inductive effect?
Bottom left.
A, B, C, or D?
D.
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 Right. So we know that D is going to be 1, correct? All right.
Yeah.
What about, A, B, C, E, and F? Which one doesn't have hydrogen bonding?
It will be F.
F.
Doesn't have hydrogen bonding.
E.
Yes, correct. Why? Because there's no hydrogen being directly connected to this fluorine. So fluorine doesn't have hydrogen bonding in this situation. Okay? So E is correct. All right. Out of the other ones that have hydrogen bonding, is there a pattern with 1 or 2 of them? Does one of them have like a branch versus more linear? What
Yeah,
would
C
be
and
comparing?
F.
C and F. Okay, so before you look at C and F, compare F and A. Is one going to be less acidic because do you see what I'm saying? Like you have
It is less acidic, right?
A.
Yes, it is. This is less acidic. This would be 3, and then this would be 4. And now if we're comparing resonance over inductive effect, what do you think matters more?
Resonance matters more, so B is more acidic.
B is more acidic, yes. So B would be 6, and C would be 5. That one was easy, right? That one's not too bad. Okay, so real quick, we have time for 2 more. Rank the following in terms of basicity. All right, what I would do here, and I don't know if Eric told you to do the same thing, is that I would change this question basically up to acidity
You protonate them?
and protonate them. Yes, exactly. Pretend like they were protonated. And then just answer this question essentially backwards. Okay? So what would be my, increasing basicity? What would be my most, or increasing acidity? What would be my most acidic? The one with the carboxylic acid group. Okay? Which one doesn't have a carboxylic acid group?
C. And the last one.
No, that's the last one. Wait, no, wait.
C, yeah, no, she's right. C doesn't have
Yeah,
a carboxylic acid group. So if you want to look in this in terms of acidity, it's going to be the lowest acidity. And I should probably change the color. So acidity is going to be red, and then we'll change it back to basicity in blue. Okay, so this is going to be red first. And you can, I'm going to put it down here to not confuse you guys. C would be, or just over here, C would be 6, most basic. But let's stick to the acidity trend. What's next? Do the rest of them have carboxylic acid? Yes, they do. But now what do we look for? Carboxylic acid with some kind of inductive effect?
How about looking for the atom? Maybe it's D.
The next, it would be D. This would be D. This would be the second least acidic, or the 5th most basic. Does that make sense? Because there's no inductive effect. With A, B, and E, and F, there is an inductive effect. They all have some kind of strong electron withdrawing group pulling it. So just to move on, chlorine is 2 carbons away versus just being 1 carbon away, or being on the same carbon in this case. 1 carbon away or same carbon. So this would be 3rd most acidic. And if you're comparing fluorine to bromine, which one's going to be more acidic?
Chlorine.
Fluorine.
Bromine or
Bromine.
fluorine? Wait, no. What's going to be pulling electrons more? The more electronegative atom.
Oh, fluorine.
Fluorine's going to be more acidic. So bromine's going to be less acidic than fluorine. And because chlorine is on the same carbon, it's the inductive effect plus, how many carbons away is it? So fluorine is 1 carbon away. And chlorine's a little bit closer, so its effect is going to be a little bit stronger. Okay? And then you just basically do this backwards. So if that was 2, 3 would be 4, this would be 5, 5, 6, and 1. Wait, did I do this correctly? 1. I think I did this backwards. 1, 2, 1, 2, 3, and 4. Right? 3 and 4. If this was based on basicity, which it is, basis. And I think that's time because I have to check out. We'll finish the rest of this acidity questions and chair confirmations, and we'll finish these naming questions. I don't know if he's going to give you complex substituents. Did he say he would?
Not really.
Not really? Okay. I'll finish the other exam for Sunday, okay? And I'll post the time in I don't have access to Blackboard, so I'll tell Eric to post the time on Blackboard, if not in the group chat, okay?
Thank you.
Cool, thank you.
You're welcome.
Thank you.
See you guys.
Thank
All right?
you.
You're welcome. Take care.